So far in this subtopic we've looked at the displacement that's involved in simple harmonic motion. We're now going to take that further and look at velocity and acceleration as well. To start with though, we're going to consider again the displacement time curve for simple harmonic motion. And we've already seen that in class, what it looks like in the context of a mass on spring oscillator. But I want to just reiterate that again. So the graph of that looks like this. So we've got time on the horizontal axis and the displacement x on the vertical axis. I'm going to represent it as a sine wave, just an easy one to draw on here. So it looks something like that. And the equation for that, as we've already seen, x is equal to x naught sine omega t. Keeping in mind that this value at the top here is the value of x naught, so the amplitude of the oscillation itself. Now we know that the gradient of a displacement time graph gives us the velocity. So we can then have a look at that graph and figure out what the velocity is going to be at various points in time, and that will allow us to then produce a velocity time graph. So hopefully I'll manage to get this lined up somewhat. So if we imagine then that we've got the axes for velocity and time, so it's still time on the horizontal axis, but now we've got the velocity v. If we consider a few key points on this graph, so we're going to start off at the origin here, we'll have another look at a point at the top there, another one here, so looking at all the key points of the graph itself. And as we step through, we'll have a look at what the gradient is. So we can see at the beginning there, we've got a steep gradient. So that means we're going to have a value here somewhere. That's going to be the steepest that it is, so let's just call that V naught, similar to X naught as we had on the original graph. So we've got that point there. If we then come across to this next point, that is a gradient of 0. So we can see at that particular time there, we're going to have a velocity of 0. The next one is where the displacement time graph passes through the equilibrium position, and we can see there it's a negative gradient. It's going to be the same magnitude as the gradient initially, so we're going to have a point down the bottom here where that's going to correspond to negative V naught. And if we continue along, we've got another point here of 0 velocity, go a bit further along to this one here, and we've got maximum velocity and then 0 again. So hopefully you can see there that we've got another periodic function that we're going to produce, and if we were to look more carefully between those points, we'd see that it actually still follows that periodic shape, and hopefully you can recognize from this graph that it's now a cos function. So we get that as our result. So the general equation here is going to be that V is equal to V naught cos omega t. So there's just sort of by inspecting the graph and figuring out what the velocity time graph would be, we can actually do that more mathematically, considering that velocity is the derivative of displacement. So by taking the graph of displacement versus time, and more specifically the function that describes that graph, we can identify that the rate of change of displacement, so dx dt, is going to be our velocity. And if we go through and derive that, and if you need some help understanding this, please ask me in class, we would find that the equation is omega x naught cos omega t. Like I say, if you're not sure about how to derive that, let me know and I can go through and explain that for you. That actually gives us a function for velocity versus time that looks like that. So V is actually equal to omega x naught cos omega t. Now hopefully you can see there that if we compare this equation with the one that we wrote earlier, the cos omega t is the same. What's different is in the one previously we had V naught, now we've got omega x naught, so we can identify that the maximum velocity, V naught, is actually just omega times the maximum displacement. So V naught is equal to omega x naught. Alternatively, we saw previously that it might not actually be that the displacement is a sine function. It might be that the displacement is a cos function, so it might be x naught cos omega t. In that case, v would then be negative omega x naught sine omega t. So those graphs, the velocity graph will depend on what the initial displacement graph is, so just be aware of that. They have both of those in the data booklet, so you just need to be careful about which one you're using, so whether you're starting off with a sine graph for displacement or starting with a cos graph for displacement. Now, if we follow that one step further, we can also identify that acceleration is the derivative of velocity. So we could go through that process again and look at the graph of acceleration versus time. I'm not going to bother doing that here because it's basically the same process and yields a similar result, but we can go through and have a look at the fact that dv dt is going to be equal to the acceleration, and the derivation of that would give us negative omega squared x naught sine omega t. So this is for the original graph that we had produced above. Now hopefully you can sort of link back to that. We had that x was equal to x naught sine omega t, and you can see that that term appears here. So we've got this value here, that's actually equal to x. So we can then say that the acceleration is simply equal to negative omega squared x. So note that I'm highlighting this equation, the one above, a is equal to negative omega squared x naught sine omega t. That's not in the data booklet, but a is equal to negative omega squared x is. Now this links all the way back to what we started off with in the first video. We can identify here that since a is equal to negative omega squared x, for any given scenario omega is going to be a constant, and so from this equation we can identify that a is proportional to negative x. So the acceleration is in the opposite direction to the displacement, and it's proportional to the displacement. And the constant of proportionality is omega squared. So while we started with that relationship, it actually sort of falls out fairly neatly from the maths behind it, and we can see there that the constant of proportionality being omega squared. And we'll have a little bit more of a look at that in class, and maybe a few past exam paper questions, and start to make sense of how all of these concepts tie together.